To my right here is Sandy Ryza from Cloudera. He's well known in the Spark community. He's made a lot of contributions. He's also working on a book, Advanced Analytics with Spark, and he's going to talk to us about estimating financial risk with Spark. It's all yours.
Thank you, Pat. Can people hear me? OK. Wonderful. Just to start, I'm a big fan of interruptions in the middle. If you have questions or if I said something that was wrong, you can stop me. Raise your hand. If you're like really near those big bright lights over there, I probably won't see you, so you could just shout out really loud, and I'll listen to what you have to say. So working as a data scientist at a platform company is a kind of interesting thing, especially working finance is a very interesting vertical. If you go to, let's say, some large retailers and you tell them, oh, hey, have you guys ever thought about using data analysis to optimize your processes, take huge data sets, think about them quantitatively, use machine learning, you'll often get this look, which is the look of maybe like a 15th century swordsman when you're trying to sell them a better tank shell. And this is, of course, with due respect to all of the retailers, especially our customers who are a little more sophisticated in their data thinking than this. On the other hand, if you go to a big bank or other financial institution and tell them, have you guys ever thought about using data and math to maybe improve your business, you'll get this look, which is maybe the look that you would get if you were to go to an experienced chef and be like, have you ever thought about using pots and pans? So data, math, quantitative analysis, they're all already very core to these kind of businesses. So with that in mind, I'm not going to talk about generally, what is it like to use data and Spark in finance. Instead, I'm going to focus on a particular use case, a particular application, that has come up various times for Cloudera and its customers that I've had the opportunity to work with a number of different institutions on, and sort of talk about why the Hadoop ecosystem and Spark in particular is a great tool for this. Any questions before we go on? No. So the question that we'd ultimately like to answer is, in a reasonable circumstance, what's the most you can expect to lose? And when we say most, we're talking about the most money you can expect to lose. This is a pretty important question to large financial institutions because it really helps determine, of all the money they have, how much needs to stay as cash and how much can they use investing to turn into more money. This is also very important because regulators require it. And they don't just require it, they require a lot more on top of it. But answering this question is sort of one of the core things that government regulators are interested in when they look at banks and financial institutions. So we formalize this question back here often in terms of this statistic called value at risk. We're going to abbreviate it as VAR often in this conversation because it's often abbreviated as such. A VAR calculation, a VAR statistic, usually comes with three parameters: portfolio, a time period, and a p-value. The portfolio concerns what are the financial instruments that we're interested in thinking about. For those sort of less familiar with light finance jargon, when we say an instrument, we're pretty much talking about anything that can be owned and has value. So a stock is an instrument, a bond is an instrument, and a derivative like an option or a swap is an instrument. So we have this big portfolio of instruments, and at this current point in time, it has some sort of some amount of value, what it's priced at, and then what we're interested in is how much could this value decrease over some matter of time. Speaking of time, the second parameter here is the time period. So are we interested in how much our portfolio might decrease by tomorrow, or are we thinking how screwed would we be in a year. Last of all is the p-value. So the p-value is how extreme is the situation that we want to think about. A p-value of 5% or 0.05 means in the worst 5% of situations, what's the amount of money that we could lose? So to be a little bit more concrete, if we say our VAR, our value at risk, for some given portfolio of instruments over 2 weeks with a p-value of 0.05 is $1 million, what we're saying is at the end of 2 weeks, we think that there's a 95% chance we'll have lost less than $1 million, and a 5% chance that we'll lose $1 million or more. One of the sort of commonly criticized elements of this statistic is it doesn't tell you in those sort of 5% of situations, are you likely to just lose $1 million, or are you likely to lose like $10 bajillion? So there are other statistics like expected shortfall, also known as conditional value at risk, that tried to think a little bit more about the properties of those tails. So how do we come up with this $1 million number, saying we given these three parameters? It requires basically hypothesizing some probability distribution over the returns of our portfolio. So over here is an example of such distribution. You can see on the x-axis, it's the returns that we're thinking about. On the y-axis is just the probability density function. That little section that's shaded extra green over there is the section underneath our value at risk that constitutes, if this is a 5% VAR, that would constitute 5% of the entire probability mass of the distribution. OK, so we need a distribution like this. How do we come up with it? There's sort of three main value at risk estimation approaches that are used. The first is this one called the variance covariance method. And this is nice and very sort of pretty because it derives a solution for the value at risk analytically. You basically compute some statistics like the variances and covariances between the different instruments inside your portfolio, plug them into this equation, and out comes a number. Well, it's nice that it's really simple and easy to calculate. The problem with it is that it's often wildly inaccurate because it makes some very restrictive assumptions about the way the data works and the way that the world works. It essentially assumes that all of the instruments follow, the returns of the instruments follow a normal distribution, and that together they follow a multivariate normal distribution. Sort of a maybe even opposite approach is what's called a historical VAR. So historical VAR, if we were trying to figure out the value at risk for a portfolio, we would say, OK, let's look at the last 100 days of what happened here. Sort them by the day-to-day returns over 100 days. And if we're looking at 5% VAR, look at the five worst and say, OK, so on 5% of the last 100 days, we lost less than $1 million, so our VAR is $1 million. This is much more likely to fit the data we have, but it also makes some very restrictive assumptions, particularly that the performance that we had in the last 100 days or whatever it is going to be similar to the future performance. And fails to account for, as Nassim Taleb would call, black swan events, really, really terrible things that might happen and maybe happened 80 years ago, but didn't happen in the last 700 days. The last approach, and the one that we're going to focus on here, is Monte Carlo simulation. The idea behind Monte Carlo simulation is we come up with some sort of model for randomly generating states of the world. So our model will give us a way to take a bunch of random numbers, and then with those random numbers, turn that into some plausible scenario for what happened. And here we're going to call each one of those scenarios a trial. So then given, we run our simulation thousands, millions, billions of times. And using all the results from those trials, we can build up some sort of histogram or some sort of empirical probability distribution that allows us to understand what's likely to happen. The nice thing about the Monte Carlo approach is that we're able to encode fairly complex behavior and complex phenomena in the process that takes our random numbers and turns them into plausible scenarios. So if we think the world works in this really complicated way, we can't necessarily analytically look at that and turn that into a single probability distribution equation. We can just run all these simulations, build up an empirical distribution, look at the tail of that distribution, and see what our value at risk is. Any questions on that before we keep going? Sort of an important concept for the rest of the talk. Great. So the question then here is, how do we build up a process for turning random numbers into plausible financial scenarios? What should our model look like for this? The most common models tend to revolve around what we'd call market risk factors. The idea is that things that happen around the world or within the market have an enormous impact on the returns of our finer-grained investments, like any particular stock or any particular option. So normally when we build a Monte Carlo risk simulation, we come up with a few different market risk factors. Some might be stock indexes like NASDAQ or the S&P 500. Others might be prices of common commodities, for example, crude oil, currency exchange rates, treasury bonds, and the like. And then, given a selection of market risk factors, we need we need two things. We need a way of simulating the behavior of these market risk factors. So, tomorrow, what's the probability that they're going to have some sort of return? And then we need some way, given the returns of the market risk factors, to predict what the returns of the instruments are going to be. So, given the price of crude oil and the price of the NASDAQ, what's the price of my particular stock or bond going to be? For the sake of simplicity, we're going to use a very simple linear model here. We're going to say basically the price of of any particular instrument is a weighted sum plus a constant of the returns of the market risk factors plus some coefficients that we figure out optimally fit the data. This is a basic linear regression. There's lots of fancier stuff that we could do, and if we were at an actual bank, we certainly would do. A few of these things are, for example, we could add features into our regression that are nonlinear transformations of the market risk factors. So if we're playing around with our data, we notice that it's possibly the case that the price of our investment varies with the logarithm of NASDAQ. Then we could add a feature that's the logarithm of the NASDAQ into our regression. We can also use fancier predictive models like decision trees, even neural nets if we'd like. We can use sort of finance-specific concepts, like we can use the Black-Scholes equation if we're modeling options, and so on and so forth. For our purposes, however, we're going to stick with this nice, simple little linear model. How do we actually train that? So generally, we have not that many market risk factors, hundreds at the most, but we could have a huge number of instruments. We could have thousands, millions. It would be nice if we could train these instruments in parallel. If only we had some sort of system that would allow us to do that. Thankfully, Spark comes to our rescue here. Here's the section where I show you code and then go to the next slide really quickly before you get to see what's going on. But basically what we're doing here is we have some process that's loading up all the returns of our market risk factors. We have some process that's loading up all the returns of our instruments. These are actually really interesting parts of what's going on, but for the sake of time, we can't really get into them. We would use Spark for those as well. You're going to have to trust me that at this point, these ... include some really intelligent stuff. And we've loaded our returns, we've loaded our instruments, and we've properly cleaned all the data. We're gonna take all these guys, and we're going to use Spark to run simple linear regressions on each instrument against all the market risk factors. And this little code snippet allows us to do that in parallel. Any questions about that? Can you guys even see it? I'll take no hands as a resounding yes. So by the end of this process, we have a model for every instrument in our portfolio. So if our portfolio has 1 million different options in it, we have a little linear model with a coefficient corresponding to each factor for every instrument.
There's a question right here.
Oh, yeah, go for it. The question was, is the sample online anywhere? So we will get to that at the end. Yes. I'll tell you where. Going on. So now we have all these models, and these models basically allow us to take a set of factors and turn them into instrument returns. How do we get these factors? Where do they come from? What's a sort of reasonable way of turning random numbers into these factors? So basically, we need to be able to generate random sample vectors where each vector is a factor return, and the length of that, or each component in the vector is a factor return, and the length of the vector is the number of factors that we have. Something to pay close attention to is that the factor returns are often correlated. If the economy is doing terribly, then the GDP and NASDAQ are likely to both be suffering. So let's try to be visual about this. Let's look at the actual factors that we might be considering. Over here is an empirical distribution of US Treasury bond 2-week returns. I generated this using this Scala tool called BreezePlot, as well as this technique called kernel density estimation, which allows you to sort of look at an empirical set of values and get a nice probability density function out of them. So this, we'd like to say it looks normal in the sense that it has a single peak, but we'd have to do a little bit more statistical testing to actually verify something like this. Here's the price of crude oil 2-week returns. Sort of a general similar shape, but the tails look fairly different. So this is the point where we make another sort of huge simplifying assumption, which if we were building a real model, we might question more rigorously and do something fancier with. But we're going to say that the returns, the market risk factors, are distributed according to a multivariate normal distribution. So the multivariate normal distribution, for those who are not familiar with it, it's a probability distribution over vectors of length n. Given all the variables, the values for all the variables except for one, that variable is distributed according to a univariate normal distribution. But it's able to model correlations between the variables. So their values, when you take random samples from it, are not totally independent. Pardon me. Here's a sort of pretty plot of what the multivariate normal might look like for two variables. We have on the floor of this graph, we have x and y, two variables that are distributed according to a multivariate normal distribution. And on the up axis, we have the probability density function. We can see that this has some sort of a diagonal aspect to it that shows that there are correlations between the variables that we're trying to model. So actually, fitting the multivariate normal distribution is pretty simple. We find out the empirical means of our variables. We build up a covariance matrix, which we can do really easily with Apache Commons Math. And the covariance matrix is a n by n array. And then using these, we can basically plug them in. I should have included this here. But Apache Commons Math actually has a multivariate normal distribution implementation. So you can plug them in, and then that'll allow you to take random samples. Every time I sort of present this material, somebody asks me, when I computed var, there was this step where 5 minutes, where I used the Cholesky distribution or I used the SVD. Multivariate normal distribution handles that. Pat's telling me I got to speed up, so I'm going to chug through this stuff. Fancier, there's all this stuff you can do. Ask me about it later. I'd love to talk about it. How do we actually run these simulations? This is the part where Spark is super important. We create an RDD of seeds, and then we use each seed to generate a set of simulations. We aggregate all the results at the end. This is a simple function that will generate a random sample from our distribution and then use it to predict the returns of all the instruments, sum them all together, and that tells us the total return of our portfolio after a single trial. Then we can say, let's create an RDD of trials by running this function over and over again on our RDD of seeds. An interesting point here is that the size of the models, even if we have like 1 million instruments, it's usually fairly small. It can fit in memory on each machine. So we broadcast it everywhere. Every executor gets all the model parameters, and then we parallelize over the simulations. This is what that parallelization sort of looks like. We have a bunch of executors. Each one is running a bunch of tasks in parallel. And then each task is sequentially running trials and getting their returns. Finally, we can take the trial returns. We can cache them. We can compute our value at risk by chopping off the tail. We can compute our CVAR, or expected shortfall, by chopping off the tail and then looking at the average of stuff over there. That's all nice and beautiful. And then here is another kernel density plot that shows us what our probability distribution looks like over returns for the full portfolio given our model. There's our var right there. So a quick note before we end. var has been around for a long time. There's lots of tools that allow you to do this and risk. Why would you use Spark for something like this? I think the most important is ease of use. So Scala and Python, you can play around with them on a REPL. It's really nice. It's great for data exploration. Then you also sort of retain the performance characteristics that you care about because you can run your final model in Java or something like that. On a single platform, you can clean your data. You can fit the models, as we saw. We can run the simulations, and then we can analyze the results. It also gives us some new powers that are a lot difficult to do with existing systems and the sort of scale of simulations that are really important. We can basically save the full matrix of so imagine a matrix where all the rows are trials and all the rows are trials, all the columns are instruments. So this is if we're running 1 million simulations on 1 million different instruments, this is a trillion elements in this matrix. We can save that whole thing with Spark, given a sufficiently sized cluster. We can cache it in memory, and we can look at and really try to understand why we're getting the results that we're getting. The last question that I always get is, it's CPU bound, we're using Java. This is crazy. Why aren't we using C++? Why aren't we using GPUs? This is not a typical Hadoop IO bound operation. The answer to this is a few things. The computational bottlenecks are normally inside large matrix operations, especially with these linear models. We're doing a bunch of matrix multiplications. These can be blastified, so basically native code deals with it already. It's not happening in Java. Java can call it, and Scala can call it to GPUs just like C++. No problem there. And then also the memory access patterns here aren't really high GC inducing. We might have a lot of stuff in memory, but there's not a ton of churn in that way that the garbage collection and the managed aspects of the JVM really slow us down. So to wrap up, what if you want to do this yourself? To answer your question, what if you're interested in learning more about this? So first thing, I've started a Spark finance project that's really concerned with building finance time series and especially risk functionality on top of Spark. If you're interested in seeing some of the fancier models that are used for this kind of stuff, I highly recommend checking it out. Patches welcome, of course. And there are some examples in there that show you how to a full run of simulations like this. Also, a plug, we just wrote this book, Advanced Analytics on Spark. And there's a whole chapter in there on doing risk simulations with Spark. Even if you don't want to get this book, the repository for it is up on GitHub, and you can see a lot of the code there. I think that's all. So thanks very much.
Awesome. So we have time for 2 questions. So I'll go straight to this guy right here.
Nice presentation. Also, your blog posts up on the Cloudera blog are very explicit in this area. Are you aware of any banks that are using Spark for their Basel reporting today?
So we have had engagements with a few different banks. I can't necessarily talk about who, but yeah. So we know 1 or 2 that are have Spark in production, and then a bunch more that are looking into using Spark for Basel reporting and that kind of stuff.
Okay, one more question. Anyone? Awesome. Oh, here we go. Here's one.
How do we make lots of money with this? How do we? You and me?
The question was, how do we make lots of money with this?
I think this is more about not trying to lose lots of money.
All right.
You tell me.
Thanks, Sandy.
Thanks, Pat.